Hello, Dr. Zhang. Roger Haley here with my fluids experiment. I've set up a recirculating water system here with a small submersible pump in the tub of water there on the lower shelf. Water's dyed blue to give it higher visibility, but I'm feeding through a vinyl tubing into the 3/4 PVC conduit that you see there mounted to the wall. My conduit has manometers mounted at the upstream and downstream ends 4 feet apart. And my goal is to take a head measurement upstream and downstream and convert that head loss into a pressure variation, which I can then use in the energy equation to calculate the velocity of the flow. And of course, using our flow rate equation, we can multiply the velocity times the cross-sectional area to calculate an expected flow rate. Then we come back and compare that to our actual measured flow rate. First, I'll let you take some measurements here with me of my head loss. Got a little fluctuation there, but pretty steady at 17 3/4 on the upstream end, and the downstream end we are right at 17 inches. All right, let me get my camera set up and we'll come back and collect some water. All right, let's collect some water to get a flow rate. It's 1 gallon of water, 27.22 seconds. Okay, we've gathered data and I've written down my calculations, so let me take you through them. We used 3/4 PVC pipe, which measured 0.805 inches inside diameter. It gives us an area of 0.00353 square feet. We used a 4-foot section of pipe for our test, and our measurements were head 1, 17.75 inches, and head 2 at 17 inches. We measured a flow rate of 1 gallon in 27.2 seconds for a total of 2.21 gallons per minute. We multiplied our head loss times gamma to get a pressure variation of 3.9 pounds per square feet. And in our energy equation, we're able to eliminate several variables. We don't need a velocity head because we use a continuous diameter of pipe. Pipe was horizontal, so Z1 and Z2 go away, and there's no pump in between our test sections, so no pump losses to worry about, and no fittings of any kind mean no minor losses. So delta P over gamma is equal to our friction losses, which we know in our Darcy-Weisbach calculation is friction factor times length over diameter times velocity squared over 2g. And solving for velocity, we get delta P times T times 2g over gamma times friction factor times length, all taken the square root of. Friction factor, we use the Moody chart. We use a smooth pipe curve, and we calculated the parameter across the top of the Moody chart to be 1.6 times 10 to the negative 3 for a friction factor of 0.0315. Plugging all that into our velocity equation, we get 1.46 feet per second, or 87.8 feet per minute. And our flow rate calculation comes out to 0.310 cubic feet per minute, or 2.32 gallons per minute. By comparison with our experimental flow rate, we have a 4.7% difference, which I am very satisfied with, given these possible flaws in our actual experiment. First of all, the head measurement, you might notice in the recording, slight variation there. Might have plus or minus 1/8 of an inch on that measurement. The accuracy of my timing while gathering the water, calculating that, might have been plus or minus a second. My interpretation of the Moody chart, somewhat inexperienced there. I think I did it correctly, but that could have led to a variation, and certainly there could have been some possible imperfections in the pipe, which would mean it'd be less than smooth, and that would certainly affect our friction factor. Finally, I did notice a tiny leak at one of my manometer fittings. It was just a small drip, but that certainly could affect our pressure and or lower our flow rate. So overall, I think it was a very successful experiment that demonstrates the relationship between head loss, pressure, the effectiveness of the energy equation, and the use of the Darcy-Weisbach friction factor equation. So I just want to say thank you very much, Dr. Zhang. Enjoyed your class immensely this semester, and I hope you have a great summer.